Welcome back. In the first part of our conversation, we learned how curiosity led you into industrial automation and why understanding systems is more important than simply knowing individual technologies. Now, let's answer the question that almost every beginner has. What exactly is industrial automation? When people hear the word automation, they often imagine robots replacing humans. Is that really what industrial automation is?
That's probably the biggest misconception. Industrial automation is not about replacing people, it's about making industrial processes smarter, safer, more consistent, and more efficient. Think about something as simple as filling water bottles in a factory. If people manually fill every bottle, they'll naturally get tired over time. Some bottles may be overfilled, others underfilled. The speed changes from person to person, and maintaining the same quality throughout the day becomes difficult. Now imagine an automated filling system. Sensors detect when a bottle reaches the filling station. A controller opens a valve for exactly the right amount of time. The bottle moves to the next station automatically. Another system checks whether the cap is fitted correctly. A vision system verifies the label. Finally, the finished bottle is packed and counted. The entire process happens with remarkable precision, thousands of times a day. That's industrial automation.
So instead of one machine doing everything, it's actually many intelligent systems working together.
Exactly. One of the biggest realizations people have after entering this industry is that no machine works in isolation. Every automated factory is like a well coordinated orchestra. Each component has a specific responsibility, and everything must happen at exactly the right time. If even one instrument is out of sync, the entire performance is affected. Factories operate in the same way.
Let's break that orchestra down. What are the main building blocks inside an automated factory?
Let's start with the most important one, sensors. Sensors are the factory's eyes, ears, and sense of touch. They constantly observe the environment, they detect whether an object is present, they measure temperature inside an oven, they monitor pressure in pipelines, they measure liquid levels in tanks, they detect machine vibration before a failure occurs. Without sensors, machines would have no idea what's happening around them.
So sensors gather information. Who makes decisions based on that information?
That's where controllers come in. The controller is the brain of the automation system. It receives information from sensors. It follows program logic. Then it decides what should happen next. For example, if the bottle is present, start filling. If the temperature becomes too high, stop the heater. If the conveyor is full, slow down production. These decisions happen within milliseconds. Most industries use programmable logic controllers, commonly known as PLCs, because they're designed to operate reliably in harsh industrial environments.
Many learners also hear about embedded systems. How are they different from PLCs?
Great question. Embedded systems are computers designed for one specific purpose. Unlike your laptop, which can perform many different tasks, an embedded system focuses on doing one job exceptionally well. Your washing machine contains embedded systems. Modern cars contain dozens of embedded systems. Medical devices use embedded systems. Smart energy meters use embedded systems. Industrial robots rely heavily on embedded systems. Even many sensors themselves contain embedded processors. So, while PLCs are widely used for industrial control, embedded systems exist everywhere around us and often work alongside PLCs inside modern factories.
That explains why embedded systems are such an important part of this field. But how do all these devices communicate with one another?
Imagine trying to organize a football match where every player speaks a different language. It would be chaos. Machines also need a common language. This is where communication protocols become essential. They allow sensors, controllers, robots, drives, and computers to exchange information accurately and quickly. For example, a controller may request temperature data from a sensor. The sensor responds instantly. The controller then sends instructions to a motor. Everything happens continuously, thousands of times every minute. Without reliable communication, automation simply wouldn't work.
And where does industrial IoT fit into all of this?
Industrial IoT takes this one step further. Instead of machines only communicating with nearby controllers, they can also share information with larger systems across the factory or even across multiple locations. Imagine a factory manager sitting hundreds of kilometers away. Through industrial IoT, they can monitor production, they can see machine performance, they can identify maintenance requirements, they can compare production across multiple factories, they can receive alerts before equipment fails. Instead of reacting after problems occur, companies can predict problems and prevent them. That's one of the biggest transformations happening in manufacturing today.
We've also started hearing terms like edge computing. What exactly is an edge device?
Let's use a simple analogy. Imagine you're driving a car. If every decision had to be sent to someone sitting in another city before you could apply the brakes, driving would be impossible. You need to make decisions instantly. Edge devices work the same way. Instead of sending every piece of information to a cloud server, they process important information close to the machine itself. This reduces delays, it improves reliability, and it allows factories to respond immediately when something unexpected happens. Edge computing has become a key part of modern industrial IoT architectures.
So far, we've talked about sensors, controllers, embedded systems, communication protocols, and edge devices. But how does the factory know what's happening across the entire production line?
That's where supervisory systems come into the picture. Factories don't just need machines that can work, they also need visibility. Operators need dashboards showing production status, managers need reports, engineers need alarms when something goes wrong. Production teams need historical data to improve efficiency. Systems such as SCADA and manufacturing execution systems collect information from across the factory and present it in a meaningful way. They help businesses answer questions like how many products were produced today? Which machine caused the most downtime? Why did production slow down? Which batch had quality issues? Without this visibility, improving production becomes extremely difficult.
Listening to this, it becomes clear that industrial automation isn't a single technology. It's an ecosystem.
Exactly. That's why learning industrial automation means learning how different technologies work together. You'll explore embedded systems because machines need intelligent control. You'll study sensors because machines need awareness. You'll learn communication protocols because machines need to exchange information. You'll understand operating systems and real-time software because machines need to respond immediately. You'll discover systems integration because factories need every component to function as one coordinated system. Every topic builds on the previous one. By the end, you'll no longer see individual devices, you'll see an entire intelligent manufacturing ecosystem.
That's a perfect way to think about it. We've gone from wondering what automation actually means to understanding how modern factories combine sensors, controllers, embedded systems, communication networks, edge devices, and industrial software into one connected system. In the next part of our conversation, we'll discuss something every newcomer should hear. What does the real industry look like once you step inside? We'll uncover the myths, the surprises, the skills that matter most, and the lessons that no textbook can fully teach. Stay with us.